Okay, well, hopefully you're all here for 742, Parallel Computer Architecture. I recognize many of you from 447 or 740. Or some of you are my students also. Okay, today we're going to cover this basically. I don't think we're going to get to some fundamental concepts, but I'd like to cover course logistics, information and requirements, and give you some things to do. This will be a busy course. Hopefully it'll be an enjoyable course, but it'll be a lot of work. So hopefully you're ready for it. If you've taken my classes before, you know that, but hopefully you'll learn a lot. It'll be different from some of the other classes you've taken, especially if you've taken 447 with me. It'll be different in the sense that this will be very research-oriented. Well, I guess this is wrong. I forgot to update the slide apparently. But the reason for this student information form is for us to get to know you. And I'd like to understand what you expect from the course. So if you write more about what kind of projects you're thinking about pursuing, for example, as best as you know at this point, that would be very helpful information. Or what kind of things you would like to learn about. Because you all have background in computer architecture right now. So you should be interested in some topics. Or maybe every topic, that's also fine. But tell me about what kind of things you're excited about looking forward to in the class. That would be very useful. Of course, if you don't turn this in, you won't be graded in the class. I guess that's a failing grade. But this is true, right? You're not in this room for grades anyway. Yeah, this is an advanced graduate course. So, okay, most of you know me, but my name is Onur Mutlu. This is my email address. I guess this is what I used to look like. I don't know if I still look like that. This was actually for a talk I gave at Carnegie Mellon in 2006. This is the picture I had sent. I think that picture is still on the Calcium website associated with that talk. That was 2006 or so. That's my office, although it may change during the course of this course. Office hours are tentatively every Wednesday, 2:30 to 3:30 p.m. Or you can send me an email, make an appointment, meet me after class. And I think a lot of you know this, but I worked at Microsoft, Intel, and AMD. In fact, I spent 2 months at Intel this summer. I was going to say AMD for some reason, but doesn't matter. They're all good companies. Intel this summer, looking a lot into research and some of the future products, which are interesting. But I'm interested a lot in computer architecture and hardware-software interaction. But I have a variety of interests, and hopefully you will be doing projects in those variety of things in this course. And this is Han, who will be your TA. I guess he's located at CIC 4th floor. And these are his office hours, Monday, Friday, 3:15, 4:15. So we'll have office hours Monday, Wednesday, Friday. Feel free to stop by anytime. If you're sending email, please send it to both of us. That's a lot easier to handle than sending it to one person. Okay. Any questions so far? So you don't have the syllabus. I didn't print it out so that we don't waste trees, but you can find it online, and I'll go over some of it. It's a PDF file. I'll basically go over what are some of the goals. What do I expect from you in this course? The first goal is, this is parallel computer architecture. So we'd like to build a strong understanding of the fundamentals in parallel computer architecture and the trade-offs made in their design. You've taken 447 and 740. We've covered some of the basics of computer architecture, as well as some parallel architecture there. But this will be more focused on parallel architecture. And we'll define what parallel architecture is in the next class, probably. We'll examine how architectures are designed to exploit and extract different types of parallelism. You could argue that every architecture is parallel today, right? You've seen instruction level parallelism. That's also parallelism. And we'll cover some of that too, actually. But the course will be more focused on thread level parallelism or task level parallelism. How can you parallelize an application rather than very fine-grained instruction level parallelism, although we will still cover that. The focus, as with the other courses you've taken, or if you're new to my courses, will be on fundamentals, trade-offs, in parallel architecture design and also cutting edge research. So you'll get both of them. And you'll read papers from the 60s as well as 2012, maybe 2013 too. The second goal, which is very important for this course, is to do research in parallel computer architecture. Basically, I guess there are two ways we will do this. One is you'll conduct a literature survey of very recent papers on a topic of your choice with my guidance, and you will present that literature survey to me and Han as well as the class. And the second is there will be an open-ended research project, again defined by you, driven by you, in groups. And the goal will be to advance the state of the art. And in the past, this is true for 740 also, but it's even more true for 742. This is an even more research-oriented course than 740. In the past, a lot of groups have come up with very good ideas and published papers at top conferences, some of which you will read in this course. Okay. And the second, I guess, second sub-goal of goal 2 in terms of doing research is getting familiar with and critically analyzing research papers. It's an important skill to have, even if you're not going to do research in the future. I can tell you, I've seen this many times when I worked with industry. People who are building cutting-edge products actually follow the research that goes on in the papers. Like I was at Intel for 2 months, and people are following the research, and they're reading the papers. They're trying to take out ideas to actually implement, potentially implement in their processors. So that's how you can impact industry without being in industry, if that's the choice you will make in the future. And if you're in industry, it's very important for you to critically analyze the paper so that you can understand actually if an idea is good for your company to implement or your next product that you're architecting to implement. So it doesn't matter what job you're going to take in the future, that critical analysis skills is very important. And hopefully you will develop that during this course and by the end of this course. And I guess another skill that hopefully you will develop as part of the goal is to give technical talks on both of your survey as well as the project findings to the entire class. So hopefully it'll be fun. Anybody scared yet? Not yet? You're scared? No, you'll do well. This should be exciting. Okay. So who should take this course? I hope you're all excited about it. It's entirely optional. Nobody is forcing you to be here. I guess except if you're my student. But even then, I'm not forcing you. But we should have a talk. It's an advanced graduate course. And you should be self-motivated in this kind of course. And you should be enthusiastic about doing research in computer architecture. And that's the only way you'll make the best out of this course, actually. It's not an undergraduate course. In an undergraduate course, you don't need to be self-motivated. Somebody will be imposing deadlines on you. You'll have to do the homework, do the assignment. Otherwise, you won't get the grade. Even undergraduate courses, you shouldn't be doing it for grades. But it's an entirely different course. So set your mindset like this. I mean, all cases are, everybody is an individual, so you should talk with me if you have questions about this, but you should have done well in graduate computer architecture, or if you've taken 447 with me, you should have done well in it. It's not a graduate computer architecture course, but you have all the basics to go to 742 from 447. Okay. Well, if none of those are true, you have to convince me that you know the required basics. And you should be enthusiastic enough to work very hard, read and critically analyze a lot of research papers, because there will be a lot of reading in this course. And you will be reviewing them. We'll talk about this. And pace yourself without deadlines. Be strongly self-motivated. Because research project, even though there will be milestones, between the milestones there will be a lot of gap. And the project will be defined by you in groups of 2, and maybe under some circumstances 3. And you will need to pace yourself. You will need to ensure that you're making progress. If you leave it to the very end, last 2 days, you will not do a good research project. That's not how research works. Research works by actually thinking about the problem, trying solutions over time. And this is a 3-month, is it 3 months? I guess September, October, November. That's right, almost 3 months. You'll have almost 3 months for a research project. So you should be thinking about it right now, as I speak, I guess, what kind of research topics that you're going to explore in the course. And discover on your own. You should be enthusiastic enough for this, because the research project is essentially that. It's discovery on your own. People can guide you, advisors can guide you in terms of doing research, but they cannot force you to actually figure out a solution to a problem, right? That comes from yourself. And figuring out what other people have done also comes from yourself. I can recommend you papers, but you can do a lot more if you explore by yourself. And you should be enthusiastic enough to make a difference, hopefully. Because in the end, that's the goal in research, advancing the state of the art, coming up with new insight. That should be the goal. OK, where do you get any questions on that? OK, everything is clear then. Good. This website will be hopefully very useful. Han will be updating this website very frequently, as we've done in past courses also. Basically, syllabus is already there. There will be logistic information as we update things. Lecture notes will be posted after each lecture. Readings will be linked from there. Project info will be posted. Basically, everything will be posted there. And there will be a review site. I think it's already linked, right, Han? Where you will do your paper reviews. If you've taken 740, you've already done this. So it's going to be a similar process. But if you haven't, the idea is, I think the CS department maintains a review site, and you need to get an account there. OK, and Han will provide you that information, hopefully. Is there a password? Yes. OK, what is it, I guess? ECE742. OK, that's easy. ECE742 is the password. Write it down, because that will be the site you will need to access to do your reviews. And reviews are an important part of this course. I'll assign reviews every week, actually multiple paper reviews every week. You will see this at the end of the presentation. And you will need to enter those reviews. The reviews don't need to be long. They don't need to be pages and pages of reviews. Actually, the best reviews are relatively short, half a page, or maybe a page. But they glean the key insights and strengths and weaknesses of a paper very quickly. If you cannot explain an idea in maybe 2 sentences, then either you haven't understood the paper or the idea is worthless. That's usually the case. There are always gray areas, but usually that's ideas are like that. OK. But I think I want to ask only for the idea in the reviews. Don't get me wrong. It should be longer than 2 sentences, because there are other things associated with the review. And that's actually one of the things that I would expect from you after this course. How to read and critically analyze papers and write a review that clearly demonstrates that you've understood the paper and clearly shows what the paper's strengths and weaknesses are about. We'll talk more about this as we go. Blackboard, I think we'll use this to upload your work, and you can definitely contact us anytime to get more information, and we'll send you email too. OK, some information about the lecture times. You all know that we have Monday, Wednesday, Friday, 4:30 to 6:20 p.m. And on average, I intend to lecture 2 to 3 days, but this will be very dynamic. I'll tell you from the beginning, my travel schedule is terrible this semester. So partially, we'll work around that travel schedule. But I'll basically, usually in the previous week, I'll announce when we will have lectures. You should be ready to be here Monday, Wednesday, Friday during this time. When there's no lecture, then we might have required or optional discussions. And that's especially important at the beginning of the semester when you're forming your literature survey topics as well as research topics. It's best if you discuss together. Even if I'm not lecturing, we'll have sessions where you discuss together to figure out what research project or literature survey topic you will follow. Okay, there's tentative schedule in your syllabus, actually. This might be a good time to look at the syllabus if we can. Let's do this. Oh, this is not working, huh? Wait. Okay, none of this is working. So how do we get to the syllabus, I guess? I guess we could do it this way. Oh, there it is. Looks like I already opened it. But this is an older version. So you can access the syllabus that way. Can you see all of this? Yeah. You should read the syllabus also. Because it has links to some of the required readings. Well, we won't have a textbook for this course. These are all recommended or supplemental textbooks. There's no single best textbook for the material that I'm going to cover, because there's no textbook that covers both fundamentals and recent research, really, as far as I know. And this parallel computer architecture book is a very good fundamental book. It's huge. It's a little bit scary. But you can use that as a reference. And all of these books are at the library reserve desk. So if you don't have a copy, you can go to the reserve desk and check it out. I assume there's a limited time where you can check it out so that you don't deny service to others. And some of the, many of the assignments will be readings. But that was not the reason why I came here. Why did I come here? Okay, yeah, tentative schedule is here, right? So if you look at this, there's a tentative schedule, which will change heavily. So don't believe any of it. Just believe the topics, if you will. But even then, topics may change also, depending on what you're going to tell me, as well as some potential talks that are going to happen here at Carnegie Mellon. So if you go to the website, there's also a link to past years. So that's actually a better schedule than what I have in the syllabus. So let me open this, another tab. So this is spring 2011. It has links to pretty much everything we've done in the course. So you can go to lectures. I intend to follow, for the most part, the same schedule of these lectures. So even though I won't provide you slides for this year, you can go and see what kind of topics that we're going to cover that are coming up. I don't guarantee this, because there may be a topic that's much more relevant at that point in time that I would like to cover based on how the discussion is going. So the schedule might change, but the overall topics will not change. So as you can see, there are 27 lectures. Let's see if we can top that this year or this semester. We'll see. Okay, any questions? So that's the schedule. I guess, why is it dynamic? I'll ask you that question. Don't believe all of it, because really, that's a static schedule, right? It's determined statically. Even the last year schedule is a static schedule. You could call it a profile, right? We've already executed this course once, obtained a profile. And it's not clear if we're going to adhere to that profile this semester when we execute it. Can anybody tell me why? I make a claim here saying that systems that perform best are usually dynamically scheduled. Why is that? Why don't we want to follow the same schedule? That sounds great, right? It sounds like sure, it's a sure bet. Assuming it worked last time. No, nobody taking a chance. Nobody took 447 or 740 here. Yes.
Because we're all different inputs.
That's right. Yeah, that's one. That's an excellent point, right? We'll have different inputs this semester that we have no idea how to predict, I think, as far as I know at this point. Well, different inputs are you, everybody else who's taking the class is different. the landscape of parallel computer architecture is different from spring 2011. It's a very fast-moving field. A lot of other things have occurred since then. The talks that will be happening at Carnegie Mellon will be different. Those are all inputs to the class. This is just like inputs to a program, right? When you execute a program, you have inputs. If you have memorized what happened previously, you could execute the program much faster the next time. In fact, if you know all the inputs to the program, you can design a system that just generates the output, right? Never executes the program. The problem is the inputs are not known. They may be predictable, but you still need to verify them, right? You all learned about the concept of value prediction. So you could take that past year's profile as a potential schedule that will change. So that's one reason. I guess let's talk about static versus dynamic scheduling, because hopefully this will lead to some papers that you may want to work on. Static scheduling, this is done at compile time, right? Schedule does not change based on runtime information. I'll give you a parallel version of it, since this is parallel computer architecture. You can think of creating parallel tasks, right? When you parallelize a program, you can divide it into many tasks. And you can decide where those tasks will be executed at the time you create the tasks. That's a static schedule. Dynamic schedule, on the other hand, is done at runtime while the program is executing. You don't dictate the schedule when you create the task, but you dictate the schedule, or you form the schedule after the tasks are created based on dynamic events. And schedule can change based on runtime information. Just like instruction scheduling, right? If you look at a single-threaded program, you have instructions to schedule, or single task, let's call it. What is scheduled is instructions to different places, whereas if you have multiple tasks that execute in parallel, then the problem is to schedule those tasks, which are units of instructions. And you could do either of these dynamically or statically. If you do instructions statically, you statically schedule, the compiler statically schedules the instructions, and the hardware obeys that schedule. Right? An add that comes later than a load cannot be reordered before the load, because the compiler dictated that schedule. Right? But you know that that's not optimal for performance, right? Because what if that load took a cache miss, and you have this add that's independent? If you don't execute that add, you're losing performance. So you've seen the concept of dynamic scheduling, which is out-of-order execution, or out-of-order scheduling, if you will, within the context of a single thread. The same issue arises, well, same issue in a similar way arises in a parallel task assignment system also. Let me give you an example. Well, I guess we already talked about this, right? I've already given you the answers. I should be asking you these questions, huh? Okay. I guess before moving into the parallel part of this, what information is not available to the static scheduler? I think we already talked about this in 447 as well as 740. So let's say you have these instructions: load, add, multiply, store, divide, load, ... And the compiler scheduled it. If the compiler wants to reorder this, what information is not available to it? Yes?
Compiler will tend to be overly conservative because it doesn't know if there is a true dependency between the instructions.
Uh-huh.
And if we do it dynamically, we may actually look at the values and figure out if the instructions are independent in the order.
Okay, so good. Go one more level deeper, in the sense that which instructions, what makes the compiler not know that there is not a dependence, or there is.
Addressing
Okay.
the values in the registers.
Memory addresses, right? The compiler doesn't know the memory address unless it's statically given. Right? The dependencies between registers are known. Right? If you have an add writing into R5 and multiply reading from R5, you know that that multiply is dependent. But if this load is loading off a value in register 5 and placing into register 2, and the store is maybe loading off register 6, well, I guess it's a better example if we have another store here, right? Let's do this. The store is loading from register 6 into register 1. The compiler doesn't know if it can reorder this load over the store, because the compiler cannot guarantee, may not be able to guarantee, I should say, that the store is not going to write to the same address this load is going to read from. Because R6 and R5 are not known at compile time. They may be. If, for example, there's some code up here that sets R6 to some value that's known, and R5 to some value that's known, then the compiler would know the address. But that's usually not the case. Compiler can do other things to try to guess this information, right? It can try to narrow the range of values a register can take. This is called value range analysis. It can try to do this, but it may not be always successful, especially if you have pointers in your program. Right? A pointer is essentially an address, right? And you could write anything to that address. And then you will use that address to load a memory location later on. So memory address is not available to the compiler, right? That's one thing. What else? What else does, yes? Exactly, yes. I didn't show you a branch here, but you figured it out. Good. You have a branch here, and let's say you have a multiply here and an add here. The compiler cannot move this add or multiply here, at least easily, because it doesn't know which path this branch will go, right? Again, it can do different kinds of analysis to figure this out. And there have been many techniques that are developed to profile the program to figure out the most likely path for a branch. And the compiler can schedule the code statically based on the most likely path a branch will take. You might, actually in 740 we had covered trace scheduling, for example, at least in some incarnations of 740, or superblock scheduling. Basically, the compiler figures out the likely path of the program based on the likely directions the branches will take and schedules the instructions on that path. If the branch takes another direction, now the compiler needs to insert fix-up code because the branch went some other direction, whereas instructions were scheduled assuming that the branch would go in this direction. So now the compiler needs to add some code that needs to undo the effects of the instructions that were executed because of that assumption. Right? So that adds overhead also. And if your profiling information is not accurate, then you will, the performance can degrade. Right? The compiler can optimize the code for a particular path, assuming that the branch is going this way, whereas the branch actually may go this way all the time. Right? So you will always be executing that fix-up code. Make sense? Yeah, that's the other piece of information. What else? Is there anything else that is not available to the compiler? If you want to do a perfect static schedule. So you covered two of them. Memory addresses are unknown. This hinders the ability of the compiler to reorder loads and stores freely. The branch direction is unknown, at least for the interesting branches. Yes? Interrupts. That's, you mean exceptions or interrupts? Yeah. Yeah, that's right. That's a little bit different though, because now you're going into the system domain. Some other task needs to be scheduled to handle that interrupt. So the compiler doesn't schedule for the entire system, if you will. Some other entity needs to schedule for that. So that's not what I was looking for. But yes, that does. If you're trying to schedule for an entire system, that becomes an issue. Yes.
Does the compiler need to worry about memory latency? Like the load, it may not be in cache, or you may need to go into RAM or something.
That's right. Exactly. The latency of an operation, more generally, right? And this manifests itself badly, if you will, in case of memory or loads. And the compiler, again, has little idea as to what that latency could be, right? This load can hit in the cache, or hit in the L1 cache, hit in the L2 cache, hit in the L3 cache, hit in the L4 cache, or miss all the way out to memory. And they all have different latencies. And depending on that latency, the compiler needs to reorder instructions, right? When should it put the dependent instruction? Where should the dependent instruction go? That really depends on the latency. And if the compiler has no idea, then you have a problem. That's why dynamic scheduling overcomes that. If you have a cache miss, for example, in an out-of-order execution engine, that cache miss waits in the reservation stations while independent instructions get executed. That's different from the compiler's specified order of instructions. Yeah, that's the third piece of information, the latency of an operation. And most importantly, the memory latency. Now, it's other operations can take variable latency also. We should generalize it as variable latency operations, perhaps. If you have a multiply, for example, you could design a multiplier that provides different latencies based on the values of the operands. Right? If one of the operands is 0, you know the answer right away. You don't need to do all the multiply. That could take, that could take much shorter. And there used to be machines where that multiply with 0 took shorter than multiply with some other number. Well, multiply two numbers that are not 0. Or if multiplying with 1 again, that's a special case, right? That could be much quicker. Okay? Let's take a look at the parallel task assignment problem. Now you're all refreshed, if you will, in your static versus dynamic scheduling. But the same issue exists in parallel task assignment also. Let's say you have n tasks. Somebody created those tasks. And p processors. And n is greater than p. Do you want to assign tasks to processors statically or dynamically? Statically means your schedule is fixed when you create the tasks. Dynamically means it's adaptive. Let's take a look at the trade-offs associated with it. Static assignment, I guess I'll give you this one. It's simpler, right? If you assigned a task to a processor, you don't need to move it again to somewhere else, which means that you don't need the hardware or software support to do that movement, which simplifies a lot of things. The downside is, the trade-off is it's inefficient. This can underutilize resources when the load is not balanced across these different processors. Does that make sense? To visualize it, I guess you have, let's say, processor 0, processor 1, processor 2, and 3 is probably more than enough. And let's say you've somehow assigned 3 tasks here, 1 task here, and then 2 tasks here. Your load is not balanced, right? One processor will be idle while another processor is still processing its tasks. Even if you assign an equal number of tasks, one processor can become idle while another processor has still tasks to process. Why could that happen? Any guesses? Yes?
Takes a different amount of time for each task.
Exactly, yeah. It could take a different amount of time for each task. Even if the tasks are equal size. I guess, yeah. The different amount of time covers everything. That could happen even if the tasks are equal size, right? Equal number of instructions. Because these tasks may, for example, the data a task needs may not be in the cache of this processor. So even though you divide up the tasks such that you have 10 instructions in each task, you may still get load imbalance because these 10 instructions, when they access data, all miss in the cache, whereas these 10 instructions all hit in the cache. So there are many reasons why you can get load imbalance. And when you get load imbalance, static scheduling is inefficient because you know that one processor is idle, but you cannot schedule the task from another processor to this processor. That's where dynamic assignment is beneficial. It's more efficient. It better utilizes processors when load is not balanced. And load balance is very difficult to satisfy. If you remember 447 or 740, there are three reasons why there are three bottlenecks, if you will, in the parallel portion of a program. Right? And one was load imbalance. And you'll remind me the next two, hopefully, later. Think about it. But load imbalance is one of them. It's very fundamental. It's very difficult for the programmer to anticipate all of these effects, or even the runtime system or the static compiler to anticipate all of these dynamic effects. The problem is the dynamic events that happen, right? You don't know what will be in the cache when this task is executed, and that will cause load imbalance. Okay, and if you have a dynamic system that identifies that this processor is idle, or maybe identifies that this task, there's data in this cache, and this task is going to use that data somehow, it can schedule that task onto that processor, right, that has that data. And people have proposed systems like that, which we may cover. The downside, so you get more efficiency that way. The downside is this is more complex, right? Now you need to move tasks around to balance processor load. And there will be issues associated with it, we'll see. And it's also higher overhead. Task movement takes time, right? It can disrupt locality also. Right? Maybe it may turn out that you have a lot of tasks here queued up and they all need the data here, but this processor is idle. It has no tasks, but it doesn't have the data this task needs. The question is, do you move this task to this processor, which is idle, which can execute the task, but doesn't have the data, so it needs to pull in the data. So there's a trade-off. It's not clear when you should move the task. You need to make policy decisions to decide when to move the tasks. Okay. Just to give you an idea, this is one of my favorite examples. This is a pictorial or high-level view of a program that computes a histogram of a large set of values, if you will. You could think of this as, I guess you're counting the number of occurrences of each letter in a book. Right? You could divide the book into smaller pages, and each page can count, each task can count the occurrences of each letter in a page, right? Let's call this the local operations. And you can update a local histogram that way. For each page, or for a set of pages, a task will figure out what is the distribution of the letters in the alphabet in that page. Right? And these are all parallel tasks. In this case, each task computes a local histogram. At some point, you need to merge the local histogram with global histograms. And you could do this hierarchically, probably, with many tasks. That's one way of solving this problem. Well, in this case, the load may be imbalanced between the tasks, right? There may be some pages that are empty, if you will. Or there may be some pages that have fewer characters. Or there may be some pages that have fewer A's than B's. You don't know. It's all input dependent. And you cannot anticipate this unless you know your input perfectly. So this is one case where load imbalance arises. And I guess I'd encourage you to read this paper if you're interested in this. Maybe you'll do a project on it. It's written by Atir Suleiman that talks about how to somewhat balance the load. Not exactly, but I want to give you the idea. You can read it. Feedback-directed pipelining. It's, I think it's in PAC 2010. And Han can post a link to it. We'll have the links to papers that are referenced in lecture. But you can take a look at it. Okay. I guess let's go into a little bit more detail here. In this case, in this example, how do you schedule tasks updating these local histograms? One option could be you can assign equal number of tasks to each processor, right? You have, in this case, I guess, n processors, and you assign an equal number of tasks. Another option is to do it dynamically. And I would assert that dynamically doing it is more efficient, hopefully for reasons that should be obvious to you by now. But it's a trade-off again. Because if you have too much overhead in the dynamic scheme, you may lose performance if you don't carefully design your dynamic scheme. And let me give you an example. Because dynamic task scheduling has overhead, whereas static task scheduling does not have that kind of overhead. For example, let's take a look at this case. How do you do the dynamic test assignment with task queues? One option is you have these processors, and they all access a shared queue. And this queue, right now, let's speak abstractly. It could be in software or in hardware. This is one way of doing it. Another way of doing it is you have these queues associated with each processor, and each processor pulls a task from its own queue. And when the queue is empty, each processor invokes a procedure that steals tasks from other queues. This is called task stealing. Yeah, task stealing. When a processor's task queue is empty, it steals a task from another processor's queue. Of course, now you have choices, right? Who do you steal from? First of all, you don't even know whose queue is not empty, right? And you don't even know what is the load balance. You could keep track of it globally, but then there's another overhead associated with it. Now you need to check that data structure where you keep track of how many tasks are in each queue, right? And what is that overhead? Let's be a little bit more concrete. Let's say you're implementing this in software. That overhead is essentially an access to a global shared data structure, right? And if somebody is accessing that data structure and somebody else is updating it, what do you need to do to that data structure? Say it again? Lock it. That's right. Yeah, you need to protect it. You need to ensure mutual exclusion to that data structure because it's a shared data structure. Now there's an overhead associated with it, which means that only one thread can be accessing that data structure, reading or writing. If you have many threads or many processors, if you will, that are trying to access the data structure, now that becomes your bottleneck. You're designing the system to steal tasks, but you're spending most of your time trying to figure out whether you should steal tasks. That's a terrible dynamic system, right? That's where static assignment may work better if you have not designed your dynamic system well. So yeah, there's a lot of choices. And people have found out over years that randomized stealing actually works well. You basically randomly pick one processor, access its queue, inquire whether it's empty or not. And if it's not empty, and if it has tasks that are where the number is greater than the threshold, steal a task from there. That doesn't require any global information, and the only thing you need to lock is that particular processor's queue, right, when you access it. And the other question is how many tasks to steal, right? You need to design heuristics, because if you steal too many, now you can create more load imbalance. If you steal too few tasks, then you incur this overhead, and you may incur it again because you'll become idle again soon. Okay, so task stealing gives you dynamic balancing of computation load, but it also leads to additional communication and synchronization overhead between processors. And if you recognize, this is the second problem in the parallel portion of a parallel program, right? Second bottleneck, if you will. Parallel portion of a parallel program is not completely parallel because there are overheads. Load imbalance was one we talked about. Synchronization is the other one. And who can tell me that what is the third one? Because I don't have a slide that will talk about that. I heard something, but serial portion. But that's the serial portion. So I'm talking about the parallel portion. Serial portion, yes, obviously, it's serial, right? You have only one thread. What about the parallel portion? Let's say if you remember Amdahl's law breaks a parallel program into serial versus parallel portions. And the assumption is that parallel portion can be perfectly parallel, right? If you remember Amdahl's law, it says your speed up of the parallel portion is the fraction of the parallel portion's execution time divided by n, where n is the number of processors. This assumes that your parallel portion is perfectly parallelizable. And that's not the case because you know that there's load imbalance, you know that there's synchronization overhead, and you know that there is one more overhead. Yes? Context switching, I wasn't thinking of that. I mean, that's certainly an overhead, but that requires a different model, right? Assume that you don't have context switches. But I guess, yeah, context switching is an example of what I have in mind. What I have in mind is more fundamental than context switching. Context switching happens because you have a limited resource, exactly. So resource contention is the third one. It's fundamental. And yes, you can put context switching into that fundamental reason why parallel portion is not perfectly parallel. So three things. We will get back to this. Actually, we have gotten back to this in 447 and 740. Three reasons why your parallel part of your program is not perfectly parallel. Load imbalance, synchronization overhead, and synchronization is very similar to communication. You synchronize to communicate. And resource contention. Okay. The other issue with task stealing is you need to stop stealing if there are no tasks to steal, right? That's an interesting problem. This is like the halting problem, or theoretically, if you will. When do you stop stealing? Maybe no is too strong, but when there are few tasks to steal, you should stop stealing also because your overhead increases significantly. Okay, let's get back to these task queues. So task stealing is one way of doing this. And it happens in this kind of distributed queue system, right? And obviously, there are overheads associated with it. So which one is better? Is this global queue better than this distributed queue? So here, you don't need to steal tasks, right? Yeah. Depends on the problem. I guess that's true, yeah. Which one is better on average, you would think? What would your gut feeling indicate? Distributed queue? Yes, likely distributed queue, right? Why? Well, because, let's say, let me put it this way. As n goes to infinity, the number of processors goes to infinity, which one's better? And you have enough tasks. Then the distributed queue is very likely better, right? Because as n increases, the likelihood that a processor is trying to get a task from the shared queue increases. And if you have this shared queue, what does that mean? When a processor needs to get a task, it needs to lock the queue. Because you don't want the same task going to two processors. You will get an incorrect outcome, right? You need to keep this queue consistent, which is a shared data structure. And you need to ensure mutual exclusion again, which introduces overhead. It's the same problem. So distributed task stealing, this distributed option is, in most cases, overwhelmingly, many cases, much better than this case. But then there's another alternative, which is a hierarchical task queue. Right? Here, you may run into load imbalance issues. Instead, you can make your queue smaller, and you can have a shared data structure that stores tasks. Instead of storing all your tasks in a distributed way, store the tasks that you're currently working on in some private queues, or currently going to work on in some private queues, and store the remaining majority of tasks in a shared queue. This makes task stealing a little bit easier, right? When you're trying to steal a task, you know where to look. And hopefully, the hope is that the load is relatively balanced here because you have smaller queues. And when you need to steal a task, just lock the shared queue and get the task from there. Does that make sense? So now which one's better, A or B? I guess I'll leave you with that question because the answer is not obvious, right? The answer really depends on your queue sizes, your workload, your task sizes. What is the overhead of accessing the shared data structure? And I guess you can think about the advantages and disadvantages of all of these. We've talked about the centralized queue, and all of these enable task stealing. Right? In this case, the task stealing is not stealing, really. Or you could argue that this is also not stealing. It's really getting the tasks that you're about to execute, dynamically getting the tasks that you want to execute. OK. So there are overheads in software management. There's another question, which is, who does this assignment? Who assigns the tasks to the processors? Does the software do it, or does the hardware do it? I mean, software, of course, creates the task, and somehow they need to be communicated to hardware at some point in time. The question is, do these tasks all live in a software queue, or do you implement in hardware a queue where the software fills in? These are tasks that are going to be executed. Does that make sense? I guess we've covered this a lot in our previous courses, so I'll go through this relatively quickly. There's always a trade-off between software and hardware, and where do you partition the work is important. I guess there's another option here, which is software-hardware cooperative. And I will argue that that's the better option. But software has better scope, right? It knows all the tasks, if you will. It can perhaps more easily pick the tasks that are going to suit a different processor. But just because of that, or because it's software, it has more time overhead. It needs to make these decisions in software. Whereas in hardware, if you have a queue, you can grab the tasks right away. What does grabbing a task consist of? Depends on how your tasks are structured, but it can consist of taking the register state and loading it into the register file, right? And the context, all of the registers, architectural registers, basically. And your architectural state can be very small. If you design your system, hardware and software cooperatively, it could be just the program counter and the stack pointer, and perhaps, if you have virtual memory, the registers that are needed to do context switching, right? Depending on your tasks. It could be very thin tasks. Or it could be very large, like what you have in x86 today. It could be all of those architectural registers, all of those machine registers, context registers, system registers that you need to load when you need to load a task. So depending on how your architecture is designed, the overhead of moving a task from one place, or even storing a task in hardware, may be high. The other disadvantage of software is it's slow to adapt to dynamic events, and this is no news for you, hopefully. For example, a processor becoming idle, if you have a queue in hardware, you can easily communicate that to the queue, right? Whereas to communicate this to the task scheduler in software, you need to generate an interrupt, or maybe have another communication mechanism, which we will talk about also, hopefully. On the other hand, if you had queues in hardware, you have low time overhead, right? You can adjust or adapt to dynamic events faster. The downside, as always, it requires hardware changes. You need to somehow have these queues, which leads to area and possibly energy overhead. Although energy overhead is not clear, right? If you actually speed up your program significantly, you can reduce your energy consumption because you're cutting down the execution time of your program or system. You're reducing the idleness in your system. But this also can make things complicated because now how do you size these queues? Right? How many entries do you put in hardware? You cannot put an infinite number of entries. Ideally, you don't want to limit your software. The software should be able to create a large number of tasks, right? But maybe it's not possible to store everything in hardware. So you need to have some interface between the software and hardware, saying when the queue is full or how many entries have been used in hardware. So that's one idea that we've briefly discussed, hardware task queues. And if you're interested in this, this is an interesting paper to read. This is optional reading again, but I'll give it to you so that if you want to do a project or a literature survey on these topics. Actually, this could be an interesting literature survey topic because there are several other papers that are published recently on this kind of fine-grained scheduling, task-based scheduling in multi-core processors. This becomes a lot more interesting when you have multi-core processors where you can move the tasks quickly between different cores. Right? And this paper provides a design with hardware task queues. The basic idea is each processor has a dedicated task queue, and software fills the task queues on demand, and hardware manages the movement, stealing of these task queues. If your hardware manages, you eliminate one overhead in stealing, right? Which is locking. You don't need to go through a software lock. You still need to ensure consistency in the queue. In hardware, you need to ensure that if this processor is pulling out a task from its local queue, some other processor should not steal it. Essentially, that's a hardware lock, right? Hardware interlock that you need to have. But the overhead of that is much less than the overhead of a software lock. You don't need to access a memory location, if you will. You can add another wire saying, oh, I'm pulling out a task here. Don't touch it. And there can be a global task queue as well, right? In hardware, again, to aid the stealing in hardware. And this paper talks about some of those options. It's an interesting paper to read. It's from Intel's Microarchitecture Research Labs, or whatever they call it these days. They keep changing names, but it's from the research lab. OK. Let's see. I guess we've covered all of this, right? One thing I'll leave you with is dynamic task generation poses additional problems, because sometimes you don't even know what tasks you have statically, right? You could still do static task assignment with dynamic task generation. This is an example, which I will not go into, but this is essentially you divide a problem into subproblems, and this task is essentially solving the subproblems, and then it's creating new subproblems, if you will, based on what happens. I guess one example that I've probably given you in some other courses, you're trying to find the exit of a maze. You're at the beginning of a maze, and you're doing, I guess let me draw you. I guess I'll cover it briefly. Why not? Maybe you don't even know the structure of this. You have a big blob, if you will. And there you have something, I guess let's call it a rat, starting from this point in the maze. And there's some cheese somewhere, or exit, if you will, at the exit somewhere. And that exit is not known to the rat. And the problem is some of the locations in this grid, and it doesn't have to be a perfect grid, are basically blocked. Basically, the rat cannot move toward those directions. How do you parallelize this problem? Right? You could basically create tasks and do a breadth-first search, right, to figure out which direction you need to go. There are many ways of solving this problem, but one problem is basically one way of solving it is, based on your current location, check if you can move toward different directions. And you can check a various number of depths also, if you will. Right? Basically, you can create a task at this point. Let's say you have 3 possible options here. You can create multiple tasks that explore the space and pick the best possible one to move. Right? In this case, each task, after you create it, may generate other tasks, right? Assuming that direction is profitable, you can create. You want to create more tasks to check whether you can go down that particular direction. Right? That's one way of parallelizing this problem. And if you do it this way, then you're essentially creating tasks dynamically. And there are many problems that create tasks dynamically, because your inputs can be dynamic also. In this case, your input is kind of dynamic, because you don't know what will happen. And increasingly, programs will be written this way going into the future as we deal with data that we do not know, right? As we deal with data that's streaming into our computers. OK, that's one problem. I guess, any questions on this? Is this exciting? These are some of the problems that we will deal with. There are a lot of issues related to this. OK. So I guess what else will you learn? Let me get back to the syllabus overview. We'll definitely learn parallel computer designs, state-of-the-art as well as recent proposals, and trade-offs and how to make them. My emphasis will be on cutting-edge research. I've already given you some papers that you should look at if you're interested in those particular topics. We'll talk about research project in a lot more detail, but this is a semester-long project. And the goal is to design better architectures. I think I've already told you. You will learn how to dig out information for sure. And textbooks are really not the best sources of information in such a fast-moving field. I guess, what do I expect from you? If you've taken my course, you know what I expect. But certainly, you should learn the material and research it. Finding the original source of ideas is a very important skill, I think, because that makes you a better researcher. Do the work hard. This should be an interactive class. We're not very big. And I'll ask you questions, and I'll expect you to ask questions also. Especially things that generate discussion is important. You should probably take notes, because I will not write everything on the board or in lecture notes. Come to class on time. If I can do that, you can do it too, probably. Although I may not be able to do it all the time. So this is perhaps the most important thing I'll tell you. Start early and focus on the research project. That's very important. Don't delay it at all. You should be thinking about these right now. That's why I'm covering some of the problems right now. And if you want feedback, come to office hours. I won't necessarily give you feedback unless you solicit it. That's one difference between this course and undergraduate courses. Undergraduate courses are more structured in terms of feedback, whereas a graduate course is you're on your own, basically. And it will be tough, but hopefully you'll have a lot of fun learning and researching and creating. So I know you're not here for grades, but I guess we'll have to do this. So the research project, presentation, and poster are the biggest part of this course. 40% of the grade. Literature survey and presentation are also a big chunk, 25%. And these are essential research. Literature survey, I would advise you to actually choose the literature survey topics such that they're in line with your research project. That would make your research project better, and that will also make your survey better too. Survey will be due earlier, of course, and that will hopefully help you prepare for the research project as well. There will be an exam, and I think the tentative date is, do you remember, Han, when it was? 29th of October? That late? OK. Oh, October. That's right, yeah. Yeah, it will probably move. I said that early, I should have said. I understood November for some reason. But it will probably move. And it could be I haven't decided the format yet. It could be the first time I taught this course, it was a written exam. And some of you have taken my written exam, so you all like it, I know. The next time I taught the course, it was an oral exam. And you can talk to some previous students about how it was. I actually met some of my previous students from that course out of all places in Seattle. And they still remember that exam. They enjoyed it a lot. This time it could be a take-home exam. I I haven't decided yet, but you can feel free to give me your input. There'll be reviews. This is mostly for your learning. This is just like homeworks that you did for 447, even though it'll be part of your grade, but the reviews are really for your benefit to critically analyze and evaluate research papers. And I guess there should be class participation. Maybe quizzes and assignments. That should be fun, no? No? Okay. It's always good to figure out what you know and what you can clearly describe when prompted, right? That's a good experience, I think. So it might happen. Grading will be back-end heavy. So be prepared for that. I'm telling you early on, there won't be much feedback, and your grade will not be determined until very late. And part of it will be, how you prepare and manage your time is for that reason very important, because this is a project-based course, and project will end at the end of the semester, at the final exam time. That's when your project reports are due. Okay? But you're not here for grades anyway, so don't be obsessed about the slide. Okay. Some policies, no late assignments are accepted, unless I extend the deadline, but hopefully that won't happen often. Everything must be your own work. This means your group work when you're doing it in groups, unless we otherwise specify. And projects and literature surveying should be done in groups. So groups of 2 and maybe 3. So if you decide to have a group of 3, you'll have to let me know quickly. So that we'll decide if I allow it, first of all. And the second is, a group of 3 is different from a group of 2, right? I hope you know what that means. Which means that if someone is doing a project by themselves, let's say a group of 1 themselves, they'll be getting more work. So you'll have to justify a bigger project, if you will. Okay. And I hope I won't have to tell you in such an advanced course, cheating means failing grade. We don't cheat. And there are no exceptions. Okay, this is the fun part. Any questions before we cover what assignments you will do for next week? All right. So the first assignment, which I'll go into more detail, is I'll give you some flexibility in this assignment. I'd like you to take 2 papers. Actually, let's go into it. That's the first assignment. It's due September 11, 11:59 p.m. Eastern time. We're in the Eastern time zone, right? Okay. Yes. That gets confusing sometimes. Basically, you can pick any 2 papers from ISCA 2012 proceedings that satisfy these requirements. It cannot be a paper you have co-authored. And at least one of them should be new to you, meaning you should not have read it. I cannot enforce this, of course, but you should not have read that paper before. And basically, you will take those 2 papers, read them thoroughly, write a critical review for each paper online, and enter the reviews in the online system. Make sense? Hopefully, this will. The way I would advise you to go about doing this is basically take the ISCA program. I guess we could do it right now together, which is conveniently linked from here. There you go. For those of you who don't know, ISCA is one of the premier architecture conferences. It's an international symposium on computer architecture. And you could go through the papers that are published. You could even go through the sessions. Here you can see the sessions, right? Memory systems, GPUs, architectures for security. It's a wide, broad coverage program. Interconnection networks, architectures for software productivity, heterogeneity. I won't go through all of these. And go through the papers in each session. And I would advise you to read the abstracts of each paper. It's not that bad, right? It's about maybe 40 papers or so. Abstracts are short. And if you're looking forward to it, you could read the entire introduction also. That actually gives you, if the introduction is written well, that gives you pretty much whether you want to read the paper or not. And hopefully, they should be written well, but that's not always the case. That's another thing you should learn from this course, how to write papers really clearly and insightfully. You will see, depending on your choices, that will not be the case in all of these papers. But basically, yeah, go through all of these abstracts. I guess the papers are not linked, but let's say we pick this paper. What you can do is you can go and search and figure it out, get it from different locations. IEEE Explorer or Digital Library of ACM is one location. And you can read the abstract of the paper and decide whether you want to review that paper. There's no particular reason I picked this paper other than randomness. And you can see that the abstract is short, right? And see if it excites you or not. And then you can read the entire paper thoroughly and write a review. But do it for the 40 papers, because that will give you a good idea of, at least in the most recent ISCA conference, what are the topics that are covered. And this could give you a good idea of what kind of topics you would like to potentially focus on your literature survey, as well as your research in this course. That's why I didn't want to dictate the papers that you will read. So hopefully this will prepare you well for the literature survey as well as the research project. And for bonus, you can pick 3 papers instead of 2. I hope some of you will do the bonus. Any questions? So that's the first assignment. The second assignment is, hopefully this should be interesting. There's an NVIDIA talk on September 10th. This is another review assignment for you. In this case, you'll review the talk. And it's also due September 11th at the same time. And this is a talk. It's actually by an EC alumnus, Philip Quadra. It's 7 to 9 p.m. Monday, September 10th. This is the new distance learning room in Hammerschlag Hall, first floor. And you can't even get refreshments. There's another bonus to it. I don't know, maybe even pizza. Do they have these? Do they have pizza at these events normally? They do? This is a tech talk. Okay. So you can get pizza. If the requirement of the assignment is not good enough of a reason to attend the talk, go for the pizza. But the talk is interesting also. I have not heard the talk. I cannot vouch for it, but it talks about the Kepler GPU architecture. And I assume it'll be more software oriented on what kind of software improvements are done to CUDA to exploit this architecture. And your job is to attend the talk and write a review of the talk. Is that good? Yes?
When did you say the review was due?
Oh, the review is due the same time as the other reviews.
Oh.
So it's 1 day later. But I would encourage you to enter it right after the talk. There's no reason not to, right? And the review website, I guess the review website, I cannot log in because I don't remember my password. But, paper reviews, if you go to the website, you'll find that linked here. And, oh, I guess I can log in with your password, right? But I need to create an account probably. Okay, you guys will be able to figure that out. Okay, so these are the 2 concrete assignments, if you will. And there are also some soft assignments, which are important still. You should start thinking hard about literature survey topics and research project topics, because the deadlines, the course move very fast. Before you know it, you will be writing the research proposal as well as literature. You will be proposing papers to survey. I think we have some dates in the syllabus, but I'll give you more up-to-date dates. And part of the reason I assigned you these papers, well, the papers you will choose, is because so that you can get thinking about these topics. Also, I would encourage you to examine survey and project topics from spring 2011. I don't have the project handout yet, but if you want to get a head start, you can go through, this is spring 2011 website. You can go through this project plus lit survey page And this has a project statement and list of ideas document, which we will update and provide more ideas. Some of these are outdated, if you will. But this is a 24-page document that describe some potential ideas and have links to papers, if you will. And these are all actually, any of these projects that you do could be cutting-edge research in the field of computer architecture. Yes?
Are the literature survey, so group 2 and project group 2, are they the same group of 2 people?
Oh, up to you.
And then are they on the same topics or?
So again, those are up to you. I would encourage you to have the same group of people, assuming you're getting along well with your partner. And I would encourage to have similar topics, because that would make your research a lot more effective. But you don't have to do that. You can pick 2 different topics if you want to learn about 2 different topics. Yes.
Literature, in that case, literature review essentially becomes like the basis for your related work.
Yes, but your related work for the project will be much more extensive than the literature survey. Okay? It cannot be just 3 papers. It should be much more extensive. Okay, so if you look at this, this is the handout from spring 2011. I will provide a handout for spring 2012, but if you want to get a jump start, which I would encourage you to do, is to go ahead and look at this handout. This will give you a good idea of what the project will look like, what the proposal will look like, what do I expect, best projects, and there are some project ideas. And this could be some of your literature survey papers also. And there are a lot of interesting topics here that are cutting-edge research in computer architecture. Okay. You can even go and look at what other people have done in the previous course. For example, Han, he took the course in spring 2011, and they reviewed these 4 papers, looks like. And looks like you have the literature review presentation also. So you could see what other people have done in the previous course. But don't pick the same papers other people have picked. I will probably challenge that decision. Okay? Okay. Well, even worse could be having the same presentation, right? Okay. And I guess this goes without saying. If you're thinking hard about this, you should find your literature survey and project partner also, if you have not already done so. And this is a small enough group that you can stay after the class and figure out who your partner is if you don't have one. Okay, so we've covered this. Don't forget the review assignments. Don't forget the talk. And I hope to be there too. So I'll be looking for you guys. Okay, I guess briefly, since you're going to be doing the reviews, I don't want to go until the end of the lecture today, but how to do the paper and talk reviews. I'm not looking for pages and pages. In fact, you should not be writing pages and pages. It should be short and concise, half a page or even shorter, but not too short that I think that it's sloppy. Okay? It should be long enough. You should try to find the right balance. So there should be a brief summary of the paper or the talk. What is the problem the paper is trying to solve? And this is a good outline for any kind of review. What are the key ideas? What are the key insights? What is the key contribution to the literature at the time it was written? Now, this won't apply to ISCA 2012 because it's written right now. But we'll be reading papers from 1970s. At that point, you should be able to identify what that contribution is. And usually good papers state their contributions. And what are the most important things you take out from it? That's kind of part of the brief summary. Strengths and weaknesses are important. Whenever you review a paper, you should be able to distill what are the strengths of the paper. And most important ones, I'm not looking for the very little nitpicks. Also, although it's fine to also include them, if you would like to include them. Strengths can come in multiple ways. Does the paper solve the problem well? That's the first thing, right? That's, if the paper provides a great, insightful idea, that's a big strength. Right? Another strength comes from the way the paper is written. These are different kinds of strengths. It's a greatly written paper. That could be another strength, right? In fact, I serve on a lot of committees where we review papers, and these strengths are much more powerful if you can clearly specify them with bullet points. That's what I'm looking for here. It's okay to write a paragraph too, but if you write bullet points, these are 3 best strengths of this paper. Then you're becoming a reviewer of a paper. That's essentially what you're going to be doing. Weaknesses, this is where you should think critically. What are the weaknesses of the paper? And some of the weaknesses are writing related, right? This is a terribly written paper. I cannot understand anything from it. That could be a bad weakness, of course. You don't want to write that kind of papers. And remember, you're going to be writing a paper at the end of this course, so hopefully reading these papers will give you an experience of what are the well-written papers and what are the badly written papers. You can have a great idea, but you can destroy it by not writing well. On the other hand, you can have a mediocre idea, not that great, small, but you can write it really well and explain that concept to everybody else. The latter can be much more effective than the former, because if you don't express your great idea, then it's kind of worthless, right? I mean, it's not completely worthless, but either find some other person to express that for you or figure out how to express it. And hopefully this course will help you develop skills to express your ideas. And these skills, again, regardless of whatever job you will go to, you will need to make a case for your ideas or for your results. And these skills are very important. So okay, going back to the weaknesses, you should read critically. You should think critically. Every paper and idea has a weakness. And it's okay to have weaknesses like the paper is not well written, but I'm also looking for weaknesses related to the mechanisms. Like, why is this mechanism not a good mechanism? And every mechanism has a weakness. For example, we've seen the hardware task stealing, right? What is the weakness? It requires hardware changes. It requires this overhead. It requires this policy. It sometimes may perform not well, right? You can write a bunch of weaknesses. And every paper also has a strength. Okay, weaknesses doesn't mean that the paper is necessarily bad. Everything is a trade-off in engineering, and the paper may be making one trade-off, whereas not optimizing for some other metric, if you will. Right? So this means that there is room for future research and improvement. So it's very important to identify weaknesses, because that could be one way for you to start your research project. Right? If you identify an important weakness in a paper, and if you have a good idea of how to solve it, and if the problem is important, of course, assuming the strengths are important, then you can propose a research project related to that. Yes?
Sometimes the authors themselves point out that the ideas are not applicable in their situations.
Mm-hmm.
So we should ignore the weaknesses.
I mean, you can certainly write them, but I'm more looking for weaknesses that you come up with on your own. So the authors, if the authors are great, that they point out every single weakness in their mechanism, which usually is not the case, and you cannot come up with a new weakness, that's fine. But usually it is the case that the authors may point out some weaknesses, but there may be some other weakness that you see in the paper. So those are more valuable, because that makes you think more critically beyond what the authors have done. Right? True for the contributions also, if the authors may not have seen a contribution, which is less likely to be the case, right? Because the authors are actually promoting their idea. Right? It's less likely that they're going to miss their contributions. Yeah.
So to mention the weaknesses in the fields for which the idea is not by presenting a paper, they cannot necessarily solve it as a use case.
Mm-hmm.
But in the current context, that may be the possible use case, but it fails.
Sounds like fun, right? You could do this for everything, actually. It's not only scientific papers. You could do this for a novel, too. Okay, some advice when doing the reviews: be very critical. That's important. That's how you advance the field. Always think about better ways of solving the problem or related problems, and do background reading if necessary. Right? In fact, reviewing a paper or a talk is the best way of learning about a research problem and topic, because that forces you to go and look at the references of the paper, do some background reading. Of course, you will have limited time. You won't be able to do a breadth first or depth first search into the background reading. But if you can do this, this will enable you to get more out of these reviews and readings. And think about forming a literature survey topic or a research proposal based on the papers you review. And GPUs can be another topic, actually. If this talk inspires in you some research topics related to GPUs, that's a perfect fit for this course, too. OK, let's see. Literature survey, I don't want to talk about this now, but more information will come here. If you read a lot of papers, you'll find a lot of good topics. Let's see. I guess I'll briefly cover this. Research project. I see this as a chance for you, if you will. It's a chance for you to explore a topic that's exciting to you and interesting to you. So you should try to pick those topics that are exciting and interesting. And second, it's your chance to publish your innovation in a top computer architecture or systems conference. And there have been many examples from 740 and 742 where this happened. In fact, I think Han finally published his paper, right? That started out as a project in 740 2 years ago. Yeah. And at that time, the idea was not there. The idea came about while they were doing their project during the course. So this is an opportunity in that sense, not only about learning about research, but also contributing to the field. And I guess I've already said this many times. Interact with me, definitely, if you want guidance on your project. You can interact with Han. You can interact with my students also. I will tell my students to be available because they're working in the field and they can provide you with potential research projects. In fact, some of the research projects that we will have in the handout that will come about will be some of the projects proposed by them. This will be done in groups of 2, and if you convince me, it could be 3. And the proposal is due September 21st. I guess today is September 5th, so you still have a lot of time. But that's not a lot of time. Forget that a lot of time. It may look like a lot of time, but it's not. OK, I already told you that you should see the old website and discover topics on your own, too. So what are the goals of the research project? The main goal is really, well, other than everything else I've stated, to develop new insight. And this new insight, hopefully, is new insight to the field. That's the bar to shoot for. It may not happen, of course, because it's research, right? You may be looking for some insight, but you may not be able to get to it, especially in 3 months. But striving for that is the first step for developing that insight. Because if you don't strive for that, then you will never develop that insight, unless some random luck hits you, which is often not the case in research. You have to be prepared, as well as you have to be lucky. Yes, Louis Pasteur said, chance favors a prepared mind, right? I think you may remember this from one of my 447 lectures. If you're not prepared, you may not see the insight in work. That's why reading all of these papers enables you to do that. So there are 2 ways of getting to that insight, I think. Developing novel ideas to solve an important problem, and rigorously evaluate the benefits and limitations of those ideas. It's maybe harder, but it's a good thing to strive for. The other approach is you can take some previously proposed ideas in the papers you read and do a rigorous analysis of those ideas to solve a particular problem or multiple different ideas to solve that particular problem. And hopefully that will come up with an insightful analysis of previously proposed ideas. And you can propose potential new solutions based on the new insight that you develop. I think these are different approaches. The first approach works well if you already have an idea. Right? Let's say you're trying to solve the memory latency problem. Somehow you want to tolerate the memory latency, and you have a new idea to tolerate that. I don't know, run-ahead execution. It's not new, but you came up with a new fancy way of doing run-ahead execution. then you can go with approach 1, right? You basically implement your idea, figure out how to make it work, and evaluate it. The second approach, same problem, memory latency problem. You have no idea how to solve it. You know some good ideas, but you don't have a new idea. So what you do is you take 3 or 4 most promising ideas, let's say run-ahead execution, state-of-the-art screen prefetching, or state-of-the-art prefetching, and multi-threading. And you evaluate them in an insightful manner. And you evaluate different combinations of them. And you of course start with a hypothesis to begin with, your hypothesis. In the first approach, your hypothesis is your new idea is better, right? Implicitly, if you will. In the second approach, you should come up with a hypothesis based on the previous ideas, and then try to either prove or disprove that hypothesis. And hopefully, that analysis of multi-threading, prefetching, and run-ahead execution will give you new ideas. We can figure out that, oh, multi-threading works in this case, but it doesn't work in this case. Or run-ahead works very well in this case, and prefetching doesn't work in this case. So you should really combine them this way. And in the end, you may come up with a new mechanism. And both are fine for this course. And both are fine approaches to research also. So you'll need to choose which approach you take, I think. And the problem and the ideas need to be concrete. That's very important. You should not come up with a very high-level problem. A lot of the projects that do not do well do not define the problem clearly. You should focus your problem well. And projects that do well focus the problem very well. And you should be doing problem-oriented research, not solution-oriented research. Like, start with the problem first. OK, some outline of the research proposal. We will not go into this in detail, but this is, you need to define the problem clearly. You need to talk about, this is more related to approach 1, if you will. Novelty, why? Well, I guess novelty of the solution. Why has previous research not solved this problem? What are its shortcomings? This is more of the importance of the problem. And you will need to give a brief overview of the relevant works, if you will. That's why knowing the relevant works is important. And what is your initial idea and insight? I think this works for, actually this works for both approaches 1 and 2. This novelty is really, why should you work on this problem, if you will? What is your initial idea and insight? What new solution are you proposing to the problem? Or what new analysis you're going to do to hopefully arrive at a new idea? Why does it make sense? And how does it, or could it solve the problem better in the end? What is the main hypothesis you will test? That's important. And how will you test that hypothesis? This should be part of your research proposal. Describe what simulator or model you will use. A lot of the changes that you will make in this course will be very likely hardware changes. It's not exclusively. There have been groups that worked on software when they took this course, and they've done fine in the projects. But it needs to be related to parallel computer architecture somehow. But how will you test that hypothesis? What kind of simulator will you use? And if you make hardware changes, usually you would need to evaluate that with a simulator. There are other ways of doing it, but it may not be feasible within in a 3-month course. And what kind of initial experiments will you do? And a plan, basically. What steps will you take? What will you accomplish by milestone 1, 2, 3 is deprecated? And final report. And give us your goals. Like, what if you're really successful? What is your moonshot goal? And hopefully you're not below the 75% mark. Meaning, what will you accomplish? And all projects should be and could be described in this fashion. In fact, that's what Meyer asked people to do. Do you guys know about Meyer? I guess if you've taken 740, did we talk about this? We did. OK. Meyer, George Meyer was a scientist who was the director of DARPA in DARPA's golden years, if you will. DARPA is the Defense Advanced Research Projects Agency that catalyzed a lot of research in the United States in the 70s. And he was the director. If someone came up to him with a research idea, he would give you these questions, basically. What are you trying to do? Articulate that without any jargon. So you should be able to specify what you're trying to do without any low-level jargon. And how is it done today? What are the limits? This is the novelty part. What's new in your approach, and why do you think it will be successful? And who cares? You should probably this will hopefully come about if you describe all of these things well. And some of these are actually not relevant to you in this research project. For example, how much will it cost? You don't need to worry about that. But if you are asking DARPA or some funding agencies for money, you will need to provide that, if you will. But this is just to give you an idea of what you're writing is really what everybody expects in a research proposal. In fact, that's how you convince people that this is an important problem, right? In the end, your paper will be like this also, a different version of this, if you will. And this is a simpler version, a simplified version, I think, which is probably better. It doesn't include those costs. What is the problem? Why is it hard? How is it solved today? What is the new idea? Why can we solve it now? And what is the impact if it's successful? Okay. Some more readings. These are not required, but these are things that you can reference. And I think Han will put up all of these on the website on research, writing, and reviews. This, actually, maybe I should make this required. This is a very good talk by Richard Hamming. You guys know about Richard Hamming? Hamming codes? Yes, that's that person. A talk he gave at Bell Labs, I think after he retired, on how to do good research from his point of view. And there are a lot of gems in this. Even if you're not going to do research in the future, there are a lot of gems in terms of how you can present yourself and your ideas. This will hopefully be helpful in writing your paper. This was written by the program chairs of, I think, SOSP 1982. That's the Symposium on Operating System Principles. They reviewed a lot of papers submitted to the program, and they've decided to write this paper, how and how not to write a good systems paper. And hopefully this will be useful when you write your paper. Or if you're doing research in general, this should be a useful paper. It's a little bit outdated, but the fundamentals are still there. The task of the referee, this is a good reference for you to, this will give you a good idea of how to do reviews, paper reviews. It's more biased towards a formal process, if you will, a publication process, and more particularly a journal review process. But you can still glean insights as to how you can write your reviews. This is a presentation that I recently found, and I agree with a lot of what's written there. It's just a presentation. I don't think, maybe there's a paper version of it too. But I would definitely recommend you to read that, because it's actually a fun presentation to go through. And this is a bibliography. If you need more of these readings, then you can go refer to this. Okay, and this is an outdated bibliography, actually. I'm sure there are new papers on that. Okay, I guess before we part, this is the class schedule for this and next week. So next week we'll have full lectures. And I intend to keep you here for 2 hours, so be prepared. 2 hours each, not 2 hours total. 6 hours total. And Friday, there is a short lecture, or it could be canceled. We'll see. But you should turn in your quiz 0 regardless, either to myself or to Han, and attach your photo. Okay, next lecture, I guess just to give you an overview, if you want to get a head start on that, if you don't have enough to read, we'll cover basics of parallel processing. And at some point I may ask you reviews, but these are good overview papers of parallel processing. These are readings in computer architecture, and Han will post PDFs of these papers. And we will definitely cover some of this going forward sometime next week. Okay? Any questions? Yes?
So this lecture is going to be posted later?
Yes, this will be posted almost immediately after the lecture. Okay? So you can reference, see all the papers and what you need to do from this lecture. Okay? Anything else? Hopefully you're all excited.